Stakeholders were selected from research conducted by our team. Some key prospects include NASA, as well as SpaceX for primary purchasers due to expressed interest. Other invested parties include manufacturing companies working on materials for the system, astronauts going on the mission, ground control monitoring the mission, future manned missions as they will learn a lot from the first habitat, as well as psychologists and botanists for research purposes. Some contenders to our company include Bigelow, Boeing, Lockheed Martin, Orbital ATK, Sierra Nevada, and NanoRacks, as they have already been awarded a contract with NASA to create a habitat for Mars by the year 2030. A full requirement list would take too long, therefore this list has been condensed to the primary subjects of importance. The system must be structurally stable and survive on Mars for a total of 3 years. The system must take care of its astronauts by providing psychological and physical support through the duration of their stay. The system must be self-sustaining, as there will be no additional support from Earth once the mission has started. These requirements are a vital part of the system and have been generated due to the risks associated with a long-duration stay.
The risks of a life on Mars are great and had to be considered to the most minute detail to ensure the survival of our Martian crew. The most deadly of which include depressurization, air contamination, and the loss of life-sustaining crops. Bone loss due to a lack of gravity, solar radiation bombardment, and the loss of power in the planet's gigantic sandstorms makes the endeavor a dangerous and potentially life-threatening one. Thankfully, the concrete framing will protect the crew from deadly radiation. Independently climate-controlled units within the habitation will protect astronauts and food stores in the case of disaster, and an extensive diet of vitamins and nutrients, coupled with resistance exercise equipment, will keep the brave crew safe.
After reviewing each risk that our design would need to address, we came up with a list of needs and requirements for our system. By keeping our requirements as broad as possible, we could then assign a number of possible solutions to each one. The different possible solutions we thought of were taken from existing systems in industry or from theoretical proposals and research papers. Once we had a list of possible solutions for each requirement, we individually voted on each solution. The final solution choices were made by coming together as a team and discussing which solutions we favored and why. Once we reached a consensus on the solution we would implement, we could then move on to the next step of our design process. During the design process, we had several different calculations that had to be completed. While doing the risk assessment, needs and requirements table, QFD, and concept generation, our team decided to individually rate the different metrics. We then used a team discussion as well as calculated weighted averages to come to any final decisions that had to be made. The most calculation-heavy portion of the design process, however, was the cost estimation. We had to determine the exact amount of materials needed to build the habitat and find the prices for several items that are not normally sold to civilians. After finding the cost of our habitat, we also had to calculate a reasonable price point which accounted for inflation and profit margin.
The final design is an elegant yet utilitarian solution to habitation on the Martian surface, making use of the fast-drying and abundantly available Martian concrete. The design manages to combine both the safety and comfort of a home with the life-sustaining and independent crops of a modern green home. Simulated skylights and windows, along with a slew of entertainment products, will help astronauts maintain a healthy morale during their stay, while water recollection systems and composting maintain a full independent greenhouse. Companies will be able to rent the habitat for 3-year-long missions in the strong and structurally permanent habitat, ensuring a sustainable future on Mars and a proving ground for future endeavors on other planets. Reflecting upon the design process and what got the team to the final design, 3 main lessons were learned. When to use the functional analysis, the need for a less complex QFD, and the difficulty involved in the final concept selection. The functional analysis could have been less complex prior to building the requirements, as multiple needs could have been met with single requirements. The mistake of having an exceedingly extensive QFD with more than 3,000 cells actually made the QFD less useful, as it was so unwieldy that it made decisions more complex. Finally, concept selection was difficult due to the assumptions of different team members about design direction, a lack of previous experience, and hard to find empirical evidence due to the novelty of the project. While these lessons would not have been easy to avoid, they nonetheless helped in understanding the complexity and difficulty of the design process.